Hello everyone. In this video, we'll see how to implement a finite state machine using VHDL. We'll also check the functionality of the FSM using the test bench we wrote for it. So let's get started. We want to implement the FSM shown in this diagram. And from the state diagram, we can see that it has 7 states from S0 to S6. It has a clock input and a reset which is synchronous with the clock, and it's taking data inputs D1 and D0. It has two data inputs and it has outputs that vary from 0 to 4. So we want to implement this state diagram, this FSM using VHDL, and let's look at the code we wrote for that. So this is the code we wrote for that state diagram. As we saw, in the entity, we are declaring the input and output ports. We have a clock and reset, which are inputs. And we also have the data, which is defined as a standard logic vector of 2 bits. So we have three inputs, which is clock, reset, and data. And we're having two outputs, one to show the outputs, and that is Q. Q will display the outputs, and we have S, which displays what state we are in. So that's the declaration of the FSM. We end the entity, and then we go to the architecture. Here we declare the states. We use the type keyword and declare the state type, which has 7 identifiers from 0 to 6, which it will represent each state we have. And we are declaring the signal state, and it will hold the value for the state we are in. And next, we are creating two aliases for the input data. As we saw, the data is a standard logic vector of 2 bits. The reason we are doing this is in the state diagram, we can see that there is a lot of don't care conditions. So if we declare the aliases like data D has 2 bits D1 and D0. So creating these aliases, we can manipulate those bits individually as well as we can change the data together. So if we see the state diagram, we can see that there are a lot of don't care conditions. So we don't necessarily need to write condition for D every time. Or if we declare D1 and D0 individually, we'll have to write like if D1 equals 0 and D0 equals 0 every time. This helps to make the code really concise. We can see that later when we go through the process. So yeah, let's go to the process, and we have the process with um, clock and reset as the arguments. We'll look for the clock mainly and the reset function also. It doesn't matter, I guess, even if there is no reset, because it's a synchronous. It's a synchronous reset which comes under the clock. But still, it still works with reset, and the simulation is also working fine. We'll see that later. But these are like the two main signals we have to always observe. So in the process, we are looking for both of them, and it's mentioned that it's a rising edge FSM. So when the rising edge clock comes, it looks if the system is reset. If it's an active high reset, if the reset is high, then it goes to state S0. That's what happens whenever we reset the system. Else, if the reset is not high, that means if there is no reset, we look how the FSM functions, and we use the case and when to implement it. So when we are in state S0, if we get the data 0, 0, then we go to state 1. We can see in the diagram, if we are in state S0 and the input is 0, 0, we go to state S1 with the input with the output of 0, and we will display the state we are in. Now we are in S1. And now else if D of 0 equal 1. Okay, what this does is We are checking if the least significant digit of d is 1. So this will account for 0, sorry, d0 equal to 1. So this will account for this case. So irrespective of whether d1 is 0 or 1. So this is the don't care case. It doesn't care what d1 is. It just looks if d0 equal 1. If d0 equal 1, it should go to state 4 with the output of 4. So if d of 0 equal 1, then we go to state 4 with the output of 4, and the state is also displayed. This is why we created two aliases. So we don't need to write all these conditions. And else, if, okay, yeah, else it goes to state 5. Because here we take into account 0, 0. Here 0, 1 and 1, 1 are taken into account. So the only thing that's left is 1, 0. So that's the else condition. So if it's 1, 0, it goes to state 5 and it has the output of 2. So that's the case when we are in state 0. Similarly, we go to state 1, and here we can see uh, the first condition, like we only have to take into account d of 1 because it doesn't matter what d0 is. So if d of 1 equal 0, so we are looking at this condition. If d of 1 equals 0, then we go to state 2 and the output is 1. Else we go to state 1 with the output of 1. So there is only two conditions here. This 0x accounts for 0, 0 and 0, 1. That's taken care by this. And the else condition is 1, 0 and 1, 1. It doesn't matter whether it's 1, 0 or 1, 1. It remains in state 1 and gives us the output of 2. So we can check at the rest of the cases where rest of the states when we are in S2, S3, S4, S5, and S6. It's following the same logic. We'll just go through it fast. So S2, we go to S2, and if d equals 0, 0, then state is S6. If it's 0, 0, it's state S6 with output 2. But if d equals 0, 1, so here we have to write all the cases. So that's the advantage of using alias. We can either use it separately or we can use the standard logic vector entirely together. So if it's 0, 1, it goes to S3 with an output of 3. And if it's 1, 0, it goes to 3 again. Yeah. If it's either 0, 1 or 1, 0, it goes to 3. And if input is, what's the next case? It goes to S4. So that's the last case. It's 1, 1. So 0, 0, 0, 1, 1, 0, and the last case is else. It goes to S4. So that's the case for S2. And then we have the case for S3. In S3, the state is assigned 6. Okay, so it doesn't matter what the inputs are. See, both are don't cares. So it doesn't matter whether D0 and D1 is 0, 0, 0. It doesn't matter whatever the input is. If you're in S3, you go to S6 with an output of 4. And now the state 4 here, if S4, we can see if the LSB is 0, that is D0 equals 0, we go to S6 with an output of 0. D0 equals 0, we go to S6 with an output of 0. Else if D0 equal 1, we remain in S4 with output of 3. Else we remain in S4. So this takes care of 0, 0 and 1, 0. This takes care of 0, 1 and 1, 1. So that's S4. Now let's see S5. In S5, If DO0 equals 0, then we go to state 6. So yeah, it doesn't matter what D of 1 is. If D of 0 is 0, this accounts for 0, 0 and 1, 0. We go to state 6 with the output of 3. Else, we go to state 3 with the output of 2. That's it. And in the final state S6, it doesn't matter what the inputs are. We always go to state 0 with the output of 0. So that's the FSM code. And now let's check out the test bench written for this. So this is the test bench we wrote for the FSM, and as we can see the entity is empty because the test bench as it is doesn't have any input or outputs. We're just giving the device under test the input signals and checking for the outputs. So the FSM is the entity is empty. And let's go to the architecture. We're declaring all the input and output signals of the FSM here. Sorry, see, these all the input and outputs are declared as signals here in the architecture, and we are initializing D with 0. And here we do the component declaration. Whatever the input and output ports are, we write it just like that, and we declare the FSM as a component here, instantiate it. Then we do the port mapping. So each of the input and output ports are mapped with the signals we declared. Clock is mapped with clock, reset with reset, data with data, output Q with Q, and S which displays the states. They're also mapped. Okay, now here we go into the implementation of the clock and the reset functions. Uh, yeah, the FSM is supposed to be having a clock of 1 megahertz. So we know that if 1 megahertz is the frequency, we can get the time period like 1 by F will give 1 microsecond. So to implement a 1 megahertz frequency clock signal, we need a time period of 1 microsecond. So clock is assigned not clock after 500 nanoseconds. So this is like half the time period. So for half the time period, it will be on. For half the time period, it will be off. So this entire signal will have a time period of 1 microsecond, and thus we'll be able to implement the 1 megahertz frequency. So this takes care of the clock. And now let's look at the stimulus inputs we give. And first, the reset case. We initially reset the signal, and after one time period, we take the reset away. So initially it's 1 and then 0. And we give the rest of these inputs which we are have to test the circuit. So we are waiting until reset equals 0. So this will enable us to test for the reset as well as 0, 0 separately. If we don't wait until reset equals 0, the initial 0, 0 will come along with the reset. So we can see when we simulate it, we can see it then. So we are going to just check for all the conditions of D. We'll give one time period gap between each inputs. So that's the test bench. So let's just simulate it and see how it goes. So let's go to view. Okay, project navigator. Yeah, there it is. Project navigator. We need to have the task also. There it is. So analysis and elaboration is already done. We can just check it again. Yes, it's working. Let's see. Yes. Yeah, it's going to take a while, but let's see. Okay, the system is really slow. It's supposed to be more fast. Yeah, that's it. So that's done. And let's look at the RTO simulation. Okay, we are running out of time. Okay, so the recording stopped. I'm doing this in Microsoft Stream. It only supports like 15 minutes. So yeah, so this is the simulation. We did the simulation. Yeah, we have the output waveform here. So let's just adjust the zoom range. Let it go from 0 microsecond till what? 15 microseconds. Okay, yeah. So we can see the outputs here. We have the clock, we have the reset, we have the different inputs we give, and we can see the output and how the state changes. Let's just compare it with the state diagram we have and verify if it's correct thing. Yeah, this is it. Okay, this is real pain. Why is it going like this? Okay, okay. So let's just verify. Initially, we have the output and state is undefined because we haven't defined what the output and state will be. Initially we just give that to the input. So we have the reset, but reset is not coming into action until we go to the first clock pulse. So it's a rising edge clock. See, even though we have reset, we have still the output and state as undefined. But the moment we have the first clock, the reset comes into play, and once you reset it, it's supposed to go to S0, state 0. But it's not showing any output yet because we didn't have any outputs. It's supposed to retain whatever output it has. We'll see it later. So now we are in state 0, and at the next pulse, we should look. Yeah, this is the next rising edge. So yeah, this is what we defined to wait for reset to become 0. So this input 0 0, we also have it here. So in this clock edge, we have the input 0 in state 0. So let's see, state 0, we have input 0 0. We're supposed to go to state 1 with an output of 0. Yeah, we are in state 1 and we have the output 0. So input 0 0, state 0. We go to state 1 with an output of 0. Now we are in state 1 and we have the input of, yeah, the input is changed after this cycle ends. So now the input is 1 0 and state is 1. So S1 with 1 0, it's supposed to remain in S1 with the output of 2. So S1, yeah, it's remaining in S1. See, the next clock came, it remains in S1, so it's the same state, and we have the output of 2. Now we are in state 1 and we're giving it input of 0 1. State 1, we're giving 0 1. We should go to state 2 with the output of 1. We're going to state 2 with the output of 1, and we're in state 2, we're getting input 1 1. We're in state 2 getting input 1 1. We should go to state 4 with an output of 0. We're going to state 4, see, with the output of 0. In state 4, we're getting inputs 0. No, no, we're getting input 1 1 itself. See, the input is continuing. State 4, if the input is 1 1, it should remain in state 4 with an output of 3. It's remaining in state 4 and we're getting the output of 3. And now we are setting, now we are giving it 0 0 input again, and we are in state 4. State 4 0 0, it should go to state 6. Yeah, it should go to state 6 with the output of 0. Okay, that worked. And now we are in state 6 and it's getting input of 3. It doesn't matter what the input is, it's supposed to go to state 0. Yeah, it goes to state 0. And state 0, it was in state 6. It got the input of 0 0. It was in state 6. Let's pause it for a second. Yeah, here we are in state 4, and the input is 1 1. State 4, input is 1 1. We remain in state 4 with the output of 3. That's correct. So then we are in state 4 with an output of 0 0. We go to state 6 with an output of 0. Yeah. Now we are in state 6. Yeah, okay, we are testing this condition now. We are in state 6 with the input of 1 1. It doesn't matter what the input is, we go to state 0. And now the next text and test is 1 0. Yeah, that's fine. After 1 1 1 0, we are in state 0 with the input of 1 0. State, we are supposed to go to state 5. Yeah, we're going to state 5 with the output of 2. Yeah, and the final thing is we are giving it 0 0 again. So from state 5, if it's 0 0, we should go to state 6 with the output of 3. It's doing that. And from state 0 6, it doesn't matter, we go to state 0 again. So that's that. So we verified the test bench and the device is working properly. So that's it. Thank you. See ya.